Okay, so I'm not going to repeat my long introduction. It was the people in the audience, offline audience, benefited from being here. So I'll continue with the talk. So the talk is on the probabilistic models for safety assessment of autonomous vehicles, and this is collaborative work with several colleagues from the Intel labs in Germany. Intel launched just before COVID. They call it Intel Collaborative Research Institute. And CT were working in this institute together with 5 German universities from, and then the point was indeed to look at the difficulties, problems with the safety assessment of autonomous vehicles. So this talk is going to give you a probably slightly different perspective, using methods which have been quite successful and are still quite popular in safety assessment of traditional systems, not related to systems where some of the components rely on machine learning or artificial intelligence. So I'm just giving a bit of a context. So the talk is quite ambitious. Probably I'll have to cut some of the details because otherwise you probably are going to get really bored to hear me speak. But nevertheless, motivation, why we do it. And then I'll outline the approach, which is not to concentrate on the so-called functional safety, where the problems are seen in the fact that some of the components fail, and therefore you look at the consequences at the system level. Instead, we're saying, even if the system works perfectly well, it is really the environment which may create hazards, and these hazards in some cases may escalate to failures. So there are in fact 2 separate studies that I'll try to cover in the talk. One is to give you the basic model, which spells out the approach using stochastic activity networks formalism. And this work was presented as there is a publication. So if somebody suddenly gets excited and wants to follow it up, you can. There is a link included in the presentation to the publication, or you can contact me. I'm happy to share the text of the paper. And the second one, which is still work in progress, we are yet to finalize it and complete it, and possibly there will be a further publication, is on a more detailed model where when we are taking into account the fact that on the roads you have intersections, and then you have periods of or intervals on the roads between these intersections, and taking into account this topology of the roads gives you additional details. And we tried in the second study to take this into account, use the proprietary data set, which provides a rich data set, which allowed us to estimate quite a few of the parameters used in, you'll see, quite a complex model, and to do something useful with it. But the key, and this is a common part in both, when it comes to parameters which affect directly safety, this is the quality of the perception system, whether the obstacle on the road is recognized on time and correctly, or the quality of the so-called safety monitors, which are the solutions which are included in the AVs to deal with any eventualities and thus try to prevent accidents. So this is these parameters are very, very difficult to estimate. And in our work, we took the view that rather than looking for data sets, which even if you find them, they will be very, very limited to specific set of circumstances, we said why don't we undertake so-called sensitivity analysis and say what are these different parameters which capture the quality of the perception system. There are different failure modes. I'm going to discuss them all. The weaknesses of the safety monitors, how these different problems can affect the system of the AV as a system at the system level. So this is probably the most significant part of this work. Motivation. Safety assessment is a challenging task. There are a lot of conferences, a lot of publications, and everybody agrees that we are very far from having a comprehensive solution to the problem how to assess the safety of the cars. There are international standards. Some of you who are interested in this area may have come across. I only listed two of them. The safety of intended functionality, which is a relatively new standard, and the more mature by now ISO 26262, which is seen by many as the Bible in automotive industry. But this standard is not really dealing with the AVs per se. It is rather looking at the assessment of individual components, the so-called ECU components in the cars. And of course, there are other guidelines. In Germany, they are quite keen to accumulate in guidelines the current understanding in the area. Similarly, in the US, of course, in the UK, we have our own set of guidelines. Also, there are alternative approaches when it comes to safety. A couple of years ago, probably more than a couple of years ago, a team from the RAND Corporation came up with quite a clear model, and they essentially, this is now known among the community as driving to safety. So essentially the point is how many miles autonomous vehicle need to have driven successfully in order for us to conclude that this particular AV, or maybe the AV as artifacts, are sufficiently safe to be licensed for use on the public roads. And my colleagues have published quite a number of papers where they scrutinized the original publication by the team from the RAND Corporation and came up with the so-called conservative Bayesian assessment, where they try to put to develop a assessment framework which will be based on the amount of miles or kilometers driven without any failure, but do it in a conservative way. So whatever the uncertainty about our knowledge and so on, the conclusions that you get using these conservative methods are unlikely to surprise you in a sense of coming up with some conservative, over-optimistic predictions. And the problem that is addressed in this talk is summarized in this at the bottom, the wording in red. How can we demonstrate that the AV is safe enough to receive certification to participate in a regular traffic? And a bit of a context. Road hazards. What are the road hazards? The road hazards are situation on the road which may or may not escalate to accident. And these are beyond our control. This is really the environment in which the car is operating. But the key here to recognize, and this is what we exploit systematically in our approach, is that if there is a hazard, the chances of having an accident eventually, this is the safety-related event, are likely to be visibly higher than if you're driving in the middle of nowhere, there is nobody on the road, and therefore, even if your car fails in a very serious way, the chances of having an accident in the sense of hitting somebody is zero because there is nobody around. So this is the law. Hazards are the what causes eventually the accidents. In the absence of hazards, the likelihood of accident is significantly lower. This is what we take into account. And the second element of this work is that we look at what makes the AV different from the other safety critical system. And here the elephant in the room is obviously the perception system, the perception system based on machine learning. If your perception overlooks obstacle on the road or classifies it incorrectly, not surprisingly, the consequences of this failure are going to be, or maybe, very dramatic. The second problem, and by the way, if the perception system fails to recognize a hazard, for instance, an obstacle on the road, this is not necessarily forever, just missing it, and it stays unnoticed forever. This may be for a very short period of time, a second, maybe a couple of seconds, and eventually the perception system may recover and seize the hazard, assess it correctly. So we're trying to capture this in our models and see what are the consequences of parameters which represents the details of what is happening on the road. And the second aspect, which is somewhat touched upon, are the so-called false alarms. Perception system says there is a hazard on the road. This is strictly, one may say, not a safety-related problem. Because, okay, false alarm, you stop the car unnecessarily. How is this going to affect safety? This is strictly not true, because if you're driving on the road and there is another car behind you, and your AV suddenly, without any obvious reason, stops because the perception system decided that there was something dangerous on the road, the guy behind may not realize that you're having a false alarm and they may hit you big time. So this may lead again to an accident. So we're looking at this aspect too. Okay, again, to go a bit further, so hazards, how do we model these hazards? Luckily, in the standards, there is a very specific recommendation how this can be done. ISO 26262 is quite specific and says hazard occurs at random and lasts randomly long. So this gives us enough information to use the recommendation by the standard and put it in the probabilistic model that I'm going to show you in a minute. So we essentially use a stochastic state machine in which the state of hazard on the road is represented by a specific state, and then how long the model will stay in this particular state is a random variable, which again, the parameters of the random variable can be estimated using the available data, publicly or proprietary data. But this is conceptually very clear. We have a state, and how long we stay, the model stays in this state is governed by a probabilistic parameter. And apart from the hazard, now we say, okay, provided the hazard exists, the two situations which are effectively failure modes of the vehicle are the failures of the perception system, the two that I already outlined, overlooking an existing real hazard on the road, possibly for a short period of time. This is one failure mode. And the second is the false alarms. Perception generates fake warnings that there is a hazard on the road. And of course, the second is what about the limitations of safety monitors? Everybody says, oh, the safety monitors have to be very reliable. The question is, how reliable is good enough? Can we study by sensitivity analysis what are the implications of having probability of failure of the safety monitor 10⁻⁶, which seems quite a small number. Is it good enough? So these are the problems that we try to address. So the basic model, I think this is more or less what I already said. What we take into account, failure perception system of two kinds, and then the failures of safety monitors and false alarms. The paper is published. If somebody is interested, please go and read it. You may find it interesting. If not, at least you'll see what we have done. And now the model. After so many words explaining what the model does, this is what the model looks like. We have several states. One is the okay. There is no hazard on the road, and everything in the AV works correctly. Hazards occur with some intensity. They are random, but nevertheless, there is a stochastic process which you can study in order to see how frequently and what are the characteristics of the times, the distribution of times between the hazards. And once the hazard is occurring, the AV may recognize this hazard immediately and correctly. So this will be handled by this possibility. We end up in a state called correctly perceived hazard, or alternatively, the complementary to event is that the hazard will be overlooked. So the car will continue to drive, to be driven, without recognizing that there is a road hazard. And then the thing that I pointed out is that this may be a temporary. For a very short period of time, we may have a problem with the perception system. So again, after a short period of time, either the hazard will disappear, or it will be eventually recognized correctly, and we end up in a state which is similar to this correctly recognized, but not quite the same because some time has been lost. And therefore, the situation may be quite different from recognizing the hazard on time. And finally, to finish with this branch, we have a state, the so-called, in terms of these probabilistic models, absorbing state. This is the disaster. Accident occurs. If the accident occurs, the game is over. We're not interested to see what happens afterwards. And here, this branch captures the possibility of having false alarms. So again, from the OK, every now and then there will be a false alarm, which gets us to a completely different state. And again, from this state, a false alarm will have a possibility of having an accident. So again, here there is a possibility to go to the accident. If the hazard is recognized correctly, we may stay in this hazard for a certain period of time. And again, this period either finishes in an accident or the hazard goes away on its own. This is, after all, the hazards on the road, they occur all the time. And as drivers, we know that this is the case. So this is the model. So the four states are, or the states in these models are listed here. We have transitions between these states, and the formalism that is used to build this model is the so-called stochastic activity networks, which is a generalization of stochastic patterns, a popular formalism supported by a specific tool that was used to solve these models. And here we made simplifying assumptions just to make use of this is convenience. It doesn't have to be. We don't need to make exponential assumptions about the all time activity being exponentially distributed, but I'll show you how fitting the available data, they're not too far from exponential distribution is not too bad. But in a sense, we know that this is not real requirement. We can drop it, solve the model using Monte Carlo simulation, or rely on asymptotic solutions which eliminate the type of the distribution. You really need to have 1-2 parameters maximum in order to get very accurate approximate solution. Okay. State and then absorbing state. I already mentioned it. Now, what are we interested in? With this model, we are interested to know the probability of having an accident within a period of time of fixed length. And so the length that we have chosen for this study is, first of all, what is the probability of having an accident within 100 hours of operation? 1,100 hours of operation, or 200. So the choice of these numbers is relatively arbitrary, but what we are saying is when exactly within the 100 hours we don't care. We're interested whether at the end of this 100 hours there has been an accident. In other words, the model entered the absorbing state accident or not. And similarly for the remaining. So this, in a sense, is telling you how the time to accident, increasing it, will affect the probability of having a safety-related event, which is the entering the absorbing state of accident. By the way, this intervals 100 up to 9,100 hours of driving. It's not calendar time, it is driving. If you drive it every a couple of hours a day, this may take very long time as in calendar times. But the data that we use this to parameterize the model, and I'll explain in a minute, is from data collected by a drone on German motorways. So the range was between 100 and 130 kilometers per hour. This is the how many kilometers the car can drive per hour. So if you look at the 9,100 with this speed, this amounts to quite a significant number of miles. We're talking about almost 1 million kilometers. What is the probability of observing an accident within 1 million kilometers of driving? So case probability, the details, if somebody is interested, happy to take this offline and provide further details. Okay, so the model parameterization. So, with this model, we have quite a few things to parameterize. The rates, even though we assume the exponential distributions everywhere, there are still quite a few of them. So we need to have these parameters. Then we have case probabilities, which says either the hazard disappears or after the duration you end up in the accident state, and so on. So there are quite a few parameters. Some of these parameters can be estimated using the available data, and we use the two publicly available data sets. This is HI-D data set, is the data set which was collected by flying a drone on the motorway and collecting the cars, how the hazards were estimated. The colleagues from Intel, they use the so-called RSS. This is the responsibility sensitive safety, a concept put forward by Mobileye. Mobileye is one of the allegedly leaders in autonomous vehicles, an Israeli company acquired a few years ago by Intel themselves. And so RSS was applied on this traffic. And then whenever the rules of RSS is effectively a set of rules, wherever what means to drive safely, whenever the rules are compromised, then this analysis will flag this is a hazardous situation, and then we'll measure for how long this hazardous situation will last. So effectively, using this data set, we can quantify what is the distribution of the intervals between the hazardous situation, and then how long this hazardous situation will last. This is what we can get directly from the HI-D data set. LIFT data set is also publicly available. It is quite different, and it's really telling you what is a perception, object recognition, if you apply it to images coming from a camera driven on the autonomous cars. The image will be maybe overlooked for a while, and then eventually it will be found. So this whole point of this second data set is to allow us to see what is the duration of overlooking objects. if they exist, but the camera and the machine learning object recognition is not detecting them instantaneously. So we use this second data set as to help us with this case probabilities, this distribution. How long we spend in this state of not seeing the object on the road. How am I with the time? I should be wrapping up.
5 minutes.
Okay, so fine. I'll try to finish the first. By now, you should be clear what we have been doing. And then there are model parameters. So the ones that are estimable from the data set, I already explained how this is done. And for the remaining parameters, which are the transitions to the accident, we use sensitivity analysis. And the purpose of the sensitivity analysis, you saw, there are quite a few transitions to the accident to say which of these are important. Do we need to worry about all of them? Or maybe there are some which make a huge impact in terms of affecting the safety of the car, and some may be quite negligible. So this is what numbers, I don't expect you to follow, and therefore I'm not exactly what they are. But if somebody is interested, again, this is in the paper, spelled out, and so on. So let's look at some of the numbers. So we have a model, we did the parameterization, we do sensitivity analysis, which means that we pretend this parameter will have value so and so, then we change it to something else to see how the change of the parameter value affects the. And there are two groups. Initially, we say if the recording the assumption immediately and correctly, accident cannot occur. So we are chopping the second part. We are saying here, if we are here, this is practically set to 0. The only possibility for a real accident is to have them from somewhere here, from the lower branch. And let's see what's happening. And there are two groups. Then we re-rux even if it is recognized correctly, there still may be a probability of accident, probably with a very small value. Okay, so this first case is telling us that if we varying the probability of missing a hazard, the hazard occurs, we miss it, it impacts the safety quite visibly, but still, with this level of parameters, no probability of accident to 10 to the minus 4 or 510 to the minus 4, the safety after 9,000 hours of operation remains really modest. We're talking about 8% only. So here, the second parameter, this is interesting and potentially very useful. Machine learning is overlooking the hazard, but for a very short period of time. Based on the second data set, it was between 1 and 3 seconds. And it turned out that this very variation of between 1 and 3 seconds doesn't make much difference. Practically, the values which are assigned here, this is 1 to 3 milliseconds, the safety remains practically the same. So this is a quite practically important. So what's here? So here we had this second, if it is overlooked and eventually it is detected, how much the likelihood of accident from this delayed, detecting correctly the hazard but with some delay, how significantly it affects the safety. Again, it is visibly affecting it. The curves are quite different, but the overall, it's 4% over for 9,000 hours of operation. Again, quite a limited impact. And finally, if we allow for, this is the model of safety monitor. We say in the first three, we assume that if the hazard is recognized immediately upon occurrence, then accident cannot occur. Now we are saying, even if you do it instantaneously and correctly, we allow for a very small chance for an accident to occur. And look at these numbers, 10 to the minus 6 or 210 to the minus 6. With such a small probability, if we allow for the accident to occur, we're talking about practically accident with certainty. Compare this with the previous figures. The previous figures are here. They're practically very, very low. Now we see that this parameter is drastically affecting the safety of the car. So this is just to give you a flavor of what we have done with this study. Unfortunately, I don't have the time to finish the presentation. The presentation includes the second case study, but I'll probably skip it and maybe some other time, or will be other opportunities to do it. So to summarize, here we have, you see how many slides I prepared. To summarize, this is the model. The value of the model is that it allows you to do this sensitivity analysis and find out which problems affect safety significantly. And therefore, people may later say, if this is so critical, either I measure the parameter, the reliability of my safety monitor very accurately, but because I see even 10 to the minus 6 is not good enough, this will make my system practically unusable. I need to target the safety monitor with significantly better reliability. Or if some of the parameters, as we have seen, the overlooking for a very short period of time, the not recognizing the object on the road immediately, it's not a big deal. You can just ignore it because it doesn't make any visible impact on system safety. So I'll stop here. Hopefully it was clear what we have done. And if there are questions, I'll be quite pleased to try to answer them.
Thank you very much, Peter, for your very interesting presentation. And now we have time for question, online and offline. First one, Dr. Oleg Ilyashenko. Welcome.
Thank you, Peter, for your presentation. My question will be as follows. Did you consider different levels of automation of AV systems, or is it a black box? Automation dependency?
Okay, we didn't. Clearly, the implications here are probably the highest, full automation, but this was not really an issue for us. Even if you take an individual function, clearly, the model is about the safety as a whole. Talking about individual function is probably not acceptable. So the honest answer is no. We didn't explicitly look at these 5 or 6 levels of automation, but implicitly we are talking about the highest, where you have a full automation.
Because I was thinking about ADIS, Advanced Driver Automation System. It's about level 3. Yeah, I was thinking about that.
But the ADS level 3 is not really where the car is. So you have somebody supervising at least the driving and so on. Well, this thing obviously is we have a failure of the perception system, which eventually leads to something else, and the safety monitor cannot deal. So again, I don't want to fantasize here, but the implications are that implicitly we talked about the higher levels of automation.
Mm-hmm. And the second question is very short. What do you consider some specific implementation of AV? Or just a black box right now?
For us, it was important to have the concept spelled out in a model where the hazards, which is the environment, combined with the potential limitations, not necessarily failures, because perception, everybody knows that the perception is quite limited. 10 to the minus, what I said, 4 is unthinkable. You can't have a perception system with this level of reliability. They talk about 80% to 90% is the accuracy of object recognition. This is what is achievable. We say that even if you have several orders of magnitude better perception system, this is probably going to be a serious problem. And what was the second one?
The second one was whether do you consider any specific implementation of AV?
No, this is Intel. We are academic, we are free spirits. We just develop models and enjoy the observations. The implementation details, we're happy to delegate it to the people who want to make money. It's not our business. Sorry.
Yes, thank you. And one more question, Igor Klushnikov. Welcome.
Good afternoon. Thank you for a very interesting presentation. And my question is, you talked about hazard recognition. How many kind of hazard we use in your model? And which size of data set to deep learning was?
Okay. We don't, you probably realize that this model operates at a relatively high level of abstraction. And the beauty of it is that we didn't have to go and spell out these are the hazards that we want to take into account. The second part of my presentation would have answered to some extent your question, because in the second part, which I couldn't cover, we had different circumstances where we are again talking about the hazard. So in the second part, we consider at least 8 different hazards, and we allow for the likelihood of manifestations of these hazards to be different. Here, we simply don't know. We just say we lump everything in a single category. The hazard is there. But of course, we thought of hazards such as object recognition of the road, or the object not being properly recognized. But again, this was conscious decision made on purpose. And I don't think it's a limitation of the work, because if you have a list of hazard, whether there's 100, 200, and so on, this framework, modeling framework, can easily be expanded to deal with any number of specific hazards.
Thank you.
As a question, Artem Abakumov, welcome. Is on chat.
On the chat, let's see the chat here.
Yes, yes. On the slide 4, you have mentioned a short delay after hazard happens. Is there any possible ways to mitigate the delay?
Possibly, but based on our study, it turns out that if the overlooking the hazard is in this range between 1 second and 3 seconds, it really doesn't matter. Therefore, even if you can mitigate, this will be effort probably wasted, because it's not making any difference in terms of system safety. This is one of the most specific outcomes of this otherwise quite abstract modeling work.
Thank you.
Okay, and Artem Perepelitsyn, welcome for your question.
Okay, thank you for your really interesting report and presentation. So the question is, if it's possible to consider some maybe ecosystem of road infrastructure that provides additional information to add some extra information about the situation on the road, is it possible to add to this model such parameters and maybe information from another cars to improve the results and use an additional source of information for the model?
Conceptually, no problem. I've used the same sums for thousands and thousands of different entities. And your question points to something quite important, and with my PhD student, whom you are going to hear later this afternoon, we're looking at the cuffs, where the cuffs are communication between the vehicles, but also communication between the the vehicle and this infrastructure, which is supposed to provide additional information for situational awareness and so on. So absolutely no problem. If you have specific needs or something very specific scenario, I'm more than happy to take this offline and see what can be done and how this model can be adapted to the specific need. But the short answer is no problem.
Okay, so the model allows such kind of scaling. Okay, thank you.
Thank you. Dear colleagues, we have not enough time. Just for me, for my question.
Okay.
A very short question. What about reasons of hazard? I mean failure equipment, problem with driver, cyber attacks on vehicle-to-vehicle communication, so on.
The hazards, what we call hazards in this work, is related to the environment and only to the environment. But of course, you are right. So the hazards are things which are happen in nature. We have no control. Of course, if we extend the hazards to be cyber related hazards, then we have to deal with. But the cyber related hazards will be not creating something artificial in the world unless some divine spirit can start putting objects on the road, and they will create this artificially created hazard. This will be really changing the behavior of the components. And the components, we take them that they have certain properties, reliability in this model, reliability of the perception system, reliability of the safety monitors, and of course via cyber, these parameters can be changed to something completely unrecognizable. But this is, again, part of the framework. If they change as a result of cyber attacks, then the assessment will be very... And by the way, this is the essence of what my PhD, Arya Kosari, is going to report this afternoon.
I can say we can talk about two-level models, yes? And your presentation related to top level,
yes?
Yes. Okay,
yes.
Thank you. Any other questions? No. Thank you very much, Peter, for your presentation.
Thank you.